Trend 3 is reinforcement learning-based controls. So you have an agent that interacts with an environment, and you will see an example in a minute for that. So the agent can take some actions which will have an influence on the environment. Then you can observe the state, like the agent in the environment, and you can say, is it a good one, good state or not? So based on the observation, you can then generate a reward and use that to train a reinforcement learning algorithm that then would teach the agent how to behave in the environment in a good way. So I hope the example will make it more clear. So, and why would you want to do that? That's in situations where the system you want to control or make decisions for is highly nonlinear or uncertain. And you want to get an end-to-end solution. So the example we have here is an automatic parking example. So here, again, full system simulation. This is a car interacting in the environment, and there are some parking lots. And this one is free, and now the neural network is trained to be able to park the car in this parking spot only based on the LiDAR data. So what has been done is first to generate a lot of training data, then training the network, and the rewards were designed such that you get a punishment, for instance, if you crash with another car, and you get a reward if you manage to park the car smoothly in here. And let's see how this looks like in the full simulation. And this example is available on our website. Let's see how it behaves in action. So here the car now has seen where is the free parking lot. And now you can see the LiDAR data that was used to train the data. And here you can see the parking. So it's not entirely smooth here, but it was really a very small neural network that was trained for that. And it already performs quite well. Okay, maybe that's not, if you would park it, you might be able to park it a little bit more smoothly and maybe also more parallel to the parking lot. But I think it's quite impressive what you can do based on only LiDAR data and only with a small neural network already. And you can run this example yourself, if you go to our website. Trend number 4, which we will have a closer look at today, is our AI-based virtual sensors. So that means, for instance, for the state of charge estimation of a battery, we can have physical sensors or use Kalman filters or extended Kalman filters for that. And now we will want to replace that with a neural network. Why would you want to do that? Well, the physical sensor could be expensive, or it could be noisy and also degrading over time, such that then the information about the state of charge is not accurate anymore after some time. And for the Kalman filter, this could take too long, or it could not be accurate. So how can you do that now? With AI, you can train a model that can predict the wanted measurement using data from existing sensors. So to summarize, a virtual sensor mimics a physical sensor using data from other measurements to estimate the quantity of interest. In our case, the state of charge of the battery. So often, people would use first principle models. So based on the domain knowledge that they have about the application, or you can use data-driven models, or a combination of both. So there's not an either or. You can mix and match. Let's have a quick look on the AI megatrend. What does it mean? I guess you've heard it, so I should just have one slide on it. So artificial intelligence is any technique that enables machines to mimic human intelligence. A subset of AI is machine learning, which are statistical methods that enable machines to learn tasks from data without explicitly programming. And there are different kinds of machine learning you can look at. One is unsupervised learning, where you have no labeled data and you try to identify, for instance, some clusters of data where you can say, okay, they behave in a similar way, so you could do a classification, for instance. Or what is mostly used is supervised learning, and which is also what our example will be, is where you have labeled data. That means for the classification example, or for our state of charge example, is you have some input data and you already know for this input data, this is the state of charge. And then you train your model to learn this. Reinforcement learning, we have seen it before, which is about interaction data. And for all these tasks, you can use deep learning. And when do you call it deep learning? It's when your neural network, it has many layers, so it's very deep. So it has a lot of parameters to learn. So, and our example, as I said, is about supervised learning. We will look at machine learning tasks, methods to do the task, but also on deep learning methods. So another slide before we dive into the example. So in general, the AI-driven system design consists of 4 steps. First, you need to, collect the data and prepare the data. So if you're dealing with real measured data, there might be some data cleansing that you need to do or bring it in a different form. This is done with human insight. So this is with your knowledge about your data. Or it could also be, simulation generated data, as we have seen. Then the second step is AI modeling. So that means you train your model. And usually this is not just one, not only do it once, you try it different times with different setups, different networks. You vary the hyperparameters that you need to train. And you use hardware accelerated training for that. You might use interoperability, or we'll see that in a minute. Then, once you're happy with your model, you need to integrate it into the complex system and also test it, how it behaves in interaction with the full system. Once you're happy with that, you can deploy it then to your target device. So it could be an embedded device, or maybe you want to deploy your algorithm in the cloud or desktop. So in our example, we were looking at the deployment for embedded devices. And so sometimes, or usually, you might need to go back and do some of the steps again. Maybe also, it could be that you noticed, oh, I didn't have enough data to begin with. You need to go back and measure some more labeled data, or simulate more data. Or maybe you need to go back and work on your model, or maybe even on the simulation and test step. So this is not linear. Usually you spend some time going back and forth here. And if you're looking at the bigger picture of model-based design, what you always need to do is through the whole design step, you test your model. So in the beginning, you define some requirements that need to be met by your system that you're designing. And then you need to define the system architecture, design the subparts, and also how it behaves with the environment. Then this is implementation or deployment step. And then also you need to test, like integrate it into the full system and test the full system. So this is, in every step, you can go back and forth. In the end, your requirements need to be fulfilled. But it's important that you test every step of the way and not just in the end, once your physical system is done, because that is time consuming if you then need to go back. So make sure to test every step